So that's why these resonant converters will provide the soft switching at that instance, and we can use these converters for high frequency applications. So what is the need of high frequency application? Is it audible to you? Hello? So my voice is audible, huh? Anyone can speak?
Yes, sir.
Yes, okay.
Is getting stuck in between.
Stuck is there, huh? Oh, just no audible, huh? No, how it my voice clear is
Yes, sir,
there?
it is audible, sir.
Clarity is there, no? Okay. So high frequency applications. So what is the need of high frequency? Why we have to operate the converter in a high frequency? So actually we have passive elements. So like a transfer, inductor and capacitors. And we are using the transformer for isolation as well as for the voltage step ups and step downs. And in our most of the applications, we have those inductive nature and magnetic elements are there. So because of these high frequencies, we can reduce the core area and transformer size in the converters. So that's why we are always looking on the high frequency converters. So here these resonant converters provide the high frequency as well as the soft switching. When we go for the soft switching, the converter will get low switching losses. So switching losses less means we can improve the efficiency of the converter. So that is the main advantage of this resonant converters. So in most of the application, not only in induction heating, in uh, in our electric vehicle applications also we are using the nowadays resonant converters like LLCs. Means two inductive elements, one capacitor, one inductive element, one inductor, two capacitors, like, and two like a parallel combination, series combinations will use for the application based on that needs. So that's why these resonant converters are most applicable in all the industry applications like electric vehicles. Like when we go for the in power system analysis also, when we want to transfer the higher powers, so their transformer size may be increased very high. So we have to reduce the transformer size using the frequency, increasing the frequency. That is the main motto of these resonant converters. Just a minute. Why it is not so presentation overview. In this presentation, I'm going to present these things. These are the content in this presentation. Resonant converters. There's basic resonant converters. What are they? Those things I'll discuss here. And next one is so mainly I concentrate on the induction heating. So induction heating applications. Some resource person may explain about the different applications, but here I will discuss mostly on the induction heating applications. Whatever the main topologies are there for the multiple load applications, those things I'll discuss in this presentation. That is in so that's why introduction of induction heating I'll give, and then resonant converters for the induction heating application. This is resonant converter basics, and then resonant converter for induction heating applications and their applications and objectives and high frequency configurations I'll discuss here. Three different configurations I'll discuss, and the scope of the resonant converter configurations I'll discuss in the panel. So resonant converters. So advantage of this resonant converter is they will provide the power factor correction as well, and switching losses reduction by using the soft switching technique, and improves the efficiency. When we reduce the switching losses, efficiency automatically will improve here. And basic types of resonant converters are here. We have series parallel and series parallel combinations. So series resonant converter means in this one we use only two elements like L and C, and R will be there in that circuit. So means here we have two second order systems, and here parallel resonant converter means in this one also we use two elements like L and C. So those are the energy storing elements. When we use those passive elements L and C, then order of the system will increase. So here the series and parallel resonant converters have only one inductor and one capacitor. But in series parallel combination we can go, in that one we can use as a two elements or three elements or higher numbers of elements also we can use. So based on that, an order of the system will increase. So this is the resonant converter schemes. it has some stages. Means actually normal structure of the resonant converter, we have input source in inverter bridge and non-resonant tank circuit, and then transformer will be there. And after that we have, when we go for the EV applications, bridge rectifier will use, or if we want to use for the induction heating, there here itself we can connect the load. And bridge, after the rectifier we have to filter that DC voltage, and then we have to connect to the load whatever it is. Based on the application, different loads you can connect here. This is the structure of the resonant converter. So this is classification of resonant converters. Actually I spoke about this. Resonant converters have classified into two element, three element, or multi element. So two, when we go for the two elements, then L and C elements are connected like this, series or parallel combinations. And when we go for the three elements, there we have to connect in different manners. And multiple means more than the three elements when we connect in the circuit, that is called multi element resonant converters. So here when we go for the combination of two element converters, here this many combinations will be possible, 8 possible combinations will be there. So based on our application, we can use any one of this combination, any one of the
Sir,
tank circuit. Hello.
sir, your slides are not changing, sir. We are able to see only the title slide, sir.
This slide only. Oh.
Yeah.
Here it is changing. Why? Okay, once I'll come back.
Can you put it in PPT mode, sir?
Okay, now slide. This slide is present showing.
No, sir. It is still showing as first one only. Title page.
Just a minute. I'll. Okay, now it is changing.
Yes, sir. Now it is changing. Now it is presentation overview.
Okay, now you check. Now it is presentation overview. No.
No, sir.
Slide.
First slide. First slide again. Title.
When I am come presenting means I'll explain in this way only. Then when I am putting in slide mode, slide show, it is not changing the. No, it is changing.
No, sir. It is not changing.
What is happening? So is it visible? No, no, I can explain like this also. Otherwise, when I
Yeah.
clicking in the slides, slide show, it is not changing the slide. Why it is, I don't.
Now it is in second slide, sir. Presentation overview.
Oh, it is third resonant
Third.
converter.
Yeah. Now it is third.
Okay, I'll explain like this only. Then when I am
Okay, sir.
keeping in slideshow mode, that is not slides. These are not. Just once again, I will check with this. No changing.
No changing, sir.
No resonant
No, sir.
converter. Okay.
Yeah. Only title. Only title. You can click on individual slides like earlier. Yes, sir.
Okay. Okay. I'll explain like this. It is visible to our. No
It is
problem.
visible, sir. It is visible.
So this is up to now. I explained this is presentation overview, and this is resonant converters. Means advantage of the resonant converter means that is power factor. Just now I spoke whatever I spoke. That is, so that is power factor improvement will be there with the resonant converters, and soft switching will be there because of that switching losses reduction by using soft switching technique. And here we have different techniques, power control techniques to get the exact soft switching. But most of the resonant converters provide the soft switching because they have load have inductive nature. So inductor, if we provide the inductive means inductive nature or capacitive nature, we can get ZVS or ZCS, zero voltage switching or zero current switching. Then we can get the low switching losses. Because of that low switching losses, we'll get the higher improved efficiencies. When we operate any converter for higher efficiencies, higher frequency, then switching losses are the major impact on the converter efficiency. So basic types of resonant converters here: series parallel converters. So this is the structure of the resonant power converters. Actually here we have input source and then inverter bridge, and then we have resonant tank, and then we can operate that inverter in higher frequencies, and then we get into means switch switched mode only transformers we use, means higher frequency we are operating, so transformer side will be very less. So this is the main impact of this resonant converter. And next, rectifier will use to when if we want a DC only, means for EV application or battery charging, if we want, then rectifier will connect. Otherwise, if we want for AC only, high frequency AC like induction heating application, if we want, then just we connect the load here. And if for based on the load applications, we have to connect the filters here. So this is the classification of resonant converters based on the number of elements. Here 2 element, 3 element, and multi element converters will be there, resonant converters. In that one, 2 elements have series and parallel combination. 3 element have there based on the combination, how we are connecting the circuit and what is our application, what is the main our motto, last final desired value. Based on that, we have to connect in different manner these elements. And multi-resonant means more than the 3 elements we are connecting, means higher order system will get, but those are complex, that's why we are not go for the higher order system. So mostly we'll go with the 2 or 3 element resonant converter configurations. When we go for more than the 3 elements multiple resonant, means their inductive nature of elements are inductors are increasing, means that is also complex system, and their inductor losses and capacitor losses will increase. So that is the, and the cost of the system will increase. So cost impacts because of the inductor and capacitor will not go for higher order, higher elements. So this is that combination, two element converters. So using the 2 element converters, we can get the 8 possible combinations. So based on our application, we can connect in any manner. So here series are both elements are connected in series. One element is connected in shunt, like that we have connect. Both elements connected in parallel, means this is parallel resonant converter, like that we can connect, and we can get the desired output. So this is 3 element combinations, will get the 26 possible combinations. Based on our application, we can use any one of that. So they have every circuit have their own advantages and disadvantages. So we have to choose the proper combination for our application. So summary, this is the advantage and disadvantage of this converter I shown here. What is the need of the series resonant? Series resonant converter means those elements are connected in series, and capacitor is connected series with the transformer. So capacitor also will provide blocks the DC, and as well as this parallel resonant converter means in that one that capacitor is not there in series, that is connected in parallel, and that's why it may not be provide the blocking possibility. And in this one, when we go for the series resonant converter, they are at light load condition, variation of the load is difficult, so that is the disadvantage. But in parallel resonant converter, we get the regulation is easy, but in that one blocking capacitor is not connected in series with the transformer. And 3 element means when we go for LLC, these 3 element configurations are very popular for electric vehicle applications. So this will provide both, means no load, full load, and as well as light load conditions, means light load conditions also will provide the proper regulation of the load power. So that is the main advantage of the LLC, and it will provide the soft switching as well. So and it provide the more efficiency and control. Main problem with this SRC and PRC is that light load and full load conditions, their operation is not suit for the control application. So that's why we go for the LLCs. And CLLC means this is somewhat most 4 elements are we are connecting, that is complex, but it will reduce the switching losses more, but it have complex system and more order of the system is increased, so number of components are increased, so cost of the system will increase. So cost is the major effect and when we going for the manufacturing of the any converter. So this is the introduction about up to now that I explained about the resonant converter, different converters. So what is the need of this resonant converter for induction heating? So first I'll introduce the induction heating. What is the induction heating? And next I'll go for different configurations of induction heating with respect to resonant converter. So here induction heating introduction. So here induction heating is nothing but actually we have induction heating principle is nothing but a transformer principle, same as here. But in transformer we have primary and secondary windings, number of turns will be there. But in here induction heating we have only primary have number of turns, means whatever the coil we are using, but secondary means that is whatever the vessel or bowl we are using. But when we go for the cooking application, that is the example I am showing here. So in cooking means we have pan bottom that is act as a single turn. So EMF will be induced because of the induction process. So when we high frequency the AC supply is given to the coil, that will induce the magnetic flux will be induced, and those will be cut with the single turn of the bowl. So it will induce the EMF in that kind, EMF in that bottom of the vessel. So then heat will be generated across that because of the eddy and eddy current loss and hysteresis loss. Mainly here eddy current loss is the major effect on the eddy current loss will be more on the vessel. So heat will be generated because of that. Means bottom only heat generates here in the induction heating. That is the main advantage. So it will not generate across the coil, which bottom only heat will be produced. So what is the configuration block diagram of this? This is the block diagram of that. So AC filter, we have single phase supply will give, and AC filter will connect with that. And next power factor. Actually load is inductive nature, so our source power factor may be affected because of that. So that's why we have to provide the power factor correction also using the filter capacitor and filter inductor. We have to connect at the source side, and that is the PFC. And next we have rectifier, and then DC filter, and then DC to AC. Means actually we have need inverter, so DC we need. So here rectifier we have to use, and we need high frequency, so high frequency inverter we are using here. So high frequency only induces the high eddy current losses. So this is the induction heating, the combination. Here in this one, more majorly electromagnetic induction is there and skin effect. So actually when we are operating for higher efficiency, higher frequency, so most of the current will be flow on the surface of the conductor only. So that is the skin effect here that induces that. And this is the configuration of that. Means what is the circuit diagram, whatever I load is there, that is load will be shown like this one. So a source and coil number of turns means when it is transformer, but in our case induction heating, so here only single turn will be there. So EMF will be induced based on the electromagnetic induction principle only. So skin effect, when well known about this everyone, skin effect means that heat will be generated on the workpiece concentrated in the peripheral layer of the skin layer, only top of the conductor only it will affect. And that depends on the skin depth of the conductor. Skin depth is depend upon the switching frequency whatever we are using. So switching frequency increase means skin depth will be low. So means surface on the surface only current will, most of the current will be concentrated. So that is depend upon the resistivity and permeability also. And the power generated is also depend upon the frequency as well as the resistivity. So this is the induction heating load model. Load will be like this. Means whatever we are showing here, this is single turn, but single turn means it have some resistance as well as the inductance. So that is the inductance R equivalent and L equivalent, and that is depend upon the geometry of the piece and the permeability of the material and temperature of the material. So what is the advantage? What is the advantage of the induction heating? Actually, induction heating is the fast heating. When we go for the domestic uses, means in conventional sources of conventional sources like gas or some other things like uh, any those will be provide some other means gas. When we use it will not fast heat that, but induction heating provides the fast heating. Within 5 minutes it will generate the heat based on our application whatever we need. So and it is clean, no smoke will be produced because of the induction heating, and it is safety also. And heating can be regulated precisely. In this one, different control techniques we use, and using that we can control the temperature also. What amount of temperature we need, based on that we can provide the control technique, and higher efficiency will be there compared to the conventional techniques. Application of induction heating, that is induction cooking, melting of metals, alloying of metals. These all are applications. All applications are there, but induction heating will be work with the higher frequencies only. So that's why we have to go for the resonant converter only. And limitations. Hello, any doubt? No limitations.
No, sir. No, sir. You can continue.
Limitations. actually what is up to now we discuss the applications and advantages of the induction heating, but it has some limitations like a failure of protective devices, interference with the means when we are operating for higher we are operating with higher frequencies, so that's why it may affect the interference with the other communication, means parallel lines will be there in the circuit. So that means higher efficiency means it is EMC problems and EMI problems will occur because of this higher frequencies, and noise will be generated because of the when we are operating for higher frequencies. So from the transformer noise will be double noise will be generated, and here inductive load is inductive nature, so poor power factor will be affected, and output depends upon the type of the material. So here whatever the load we are using, that is different in domestic applications. If we go example, if we take the induction cooking, in domestic uses we use different metal vessels, like say, like aluminum vessels we use, or iron vessels we use, steel vessels we use. So they have their different properties, their metal properties are different, so with respect to frequency their properties will be changed. So those things also I'll cover in the next when we go for the configurations. So normally resonant inverter topologies are there for induction heating is full bridge resonant converter, half bridge, and single switch resonant converters. So these converters, these are we using for different means when we go for 5 kilowatt application, that is industries only we use, and for domestic users below 5 kilowatt only we use, and for actually domestic means in a home applications or in the like restaurants they are also using, but they are used for nearly about 2 kilowatt the power they will use. So these here resonant converters are there, but we have to control the power of that. So for that one we have different control techniques. I'll discuss here: frequency control, phase shift control, and asymmetric duty cycle control, and asymmetric voltage cancellation control. These are the different control techniques normally we use in resonant converters. So first one is frequency control techniques. Actually, frequency control means just we have to change the frequency, switching frequency whatever we are operating. But our resonant frequency is fixed only. So this Fs by Fr ratio will be changes. Means whenever Fs by Fr ratio switching frequency by resonant frequency changes, then output power will change. So that affects on the quality factor, and that those things I shown here. This is the output power versus quality factor with various switching frequencies. Resonant frequency is fixed only. When we connect the inductor, means inductor and capacitor at the starting, we can't regulate the inductor and capacitors. If we want to regulate the inductor and capacitor, we have to add the capacitor again. So that is using the mechanical switches we have to do. So that mechanical switch means that is again the disadvantage, that will not be fast operation. So that is the problem. But switching frequency, when we change the switching frequency, it is goes away from the resonant frequency, then resonant frequency will not be changed. So resonant frequency is fixed at some point, but switching frequency is varying, so load power will be changed based on that frequencies. Next one is phase shift. Phase shift control we can apply only for the full bridge converters. So full bridge converter means these two legs will be there and four switches will be connected, and we can shift the phase of that, means from leg 1 to leg 2. This is the leg 1 and this is leg 2. So from leg 1 to leg 2 we have to shift. This is the, in this way we have to generate the pulses, and we give to VG1 VG3 means VG1 and VG3. This is these two, actually this is S1 S2 S3 and S4. S1 and S4s are same. Actually those will, whenever these two are on, then voltage will be there, means positive magnetic voltage. Whenever these two switches are on, then voltage will be there. So like that will be there, VG1 and VG4 whenever on, then output voltage will be there here. And we are shifting this phase, means from the S1, actually S1 is on up to this point, but S4 is on some of the time, means some time we are not operating, means we are giving some delay to that S4. So because of that one delay, we'll get here some voltage difference will be there here. So based on that we can control the power. This is the phase shift. So in this one, just we control the, actually Fs by Fr ratio is constant, means we are not changing the frequency, but we are changing the duty cycle of that. Means duty cycle means we are providing some delay or phase shift, means actually phase shift will provide here. So phase shift will provide in between the switches to control the output power. So next one is asymmetric duty cycle. Asymmetric duty cycle, actually when we see here, this is a symmetrical waveform, but output voltage is symmetrical. But in this case, when we see this output voltage waveform will be asymmetrical here. So positive and negative magnitude of voltages are not equal. So this is asymmetric, but asymmetric because of the asymmetric different harmonic current, harmonic voltages and currents will be induced. But this will also provide the soft switching as well as the power control. So here in this case VG1 and VG1, this is the switch, these are same full bridge I took here. So in this one VG1 and VG4 will be same. VG1 and VG4 will be same, but VG S2 and S3, VG2 and VG3 will be different, but their on time of the VG2 means switch 2 and switch 3 will be higher compared to this. That's why this output voltage will be asymmetrical. But in this case also Fs by Fr is a fixed, so switching frequency we are not changing, so other harmonic currents will not be induced, but means multi-resonant will not be there. But resonant frequency will be fixed only, and switching frequency is also fixed, but duty cycle is changed, so average value of the voltage will be changed here. So because of that output power will be changed. So that is asymmetric duty cycle and asymmetric voltage cancellation. So here in this case also asymmetric voltage will be cancelled, and here in this case we shift the voltage. S1 and S2 will be connected here. S1 when we observe this pulses, so these are the gate pulses only, VG1, VG4, VG3, VG2. So when VG1 and VG4 should be on when we want the output voltage is positive. So here when we observe here, this is VG1 is on up to here and VG4 is on for some more time. So because of that here and this these two VG4 and VG2 are both are inverse to each other. So because of that we'll get that voltage will be cancelled here. Whenever these VG4 and VG2s are on, then short circuit will be, these two switches are on means load will be short circuited with through this. So because of that voltage will be zero here. So voltage will be zero. So that's why in that asymmetric voltage will be cancelled here. In that way also we can control the power. So in all these cases we are changing the duty cycle only. So these are the control techniques we use for the normally for the resonant converter to power control. So converter scheme for induction heating. Actually, we have different converter schemes are there. In this one, single stage, multi-stage converter schemes are there. So first one is that is multi-stages. In that one, we have rectifier, inverter, different converters are there. Even stages are there in that. Means rectifier stage is one, inverter stage is one, and filter stage is there. But in this case, we have different stages, so number of components are high. And in this case, this is the voltage source inverter and this is the current source inverters. When we use the current source inverters, then DC filter will be connected in series, and here DC filter will be connected in the shunt. And here actually resonant converter with respect to different means using the MOSFET or IGBT, or we are using SCRs or like that. Based on that one also will get different configurations. So this is the one of the scheme, but most valid scheme is no nowadays. Mostly most research is going on this single stage converter. So single stage converter means we already heard about the cyclo converters like that only, but here we have provided both. Actually rectification as well as inversion both are there in the same configuration. So that is the single stage converter. In that one, number of components will be reduced, number of switches will be reduced. So switches reduced means switching losses as well as conduction losses, everything will reduce. The cost of the system also reduces. So that is about the single stage converters. So these are the converter schemes. Now I'll explain some configurations, some of the configuration for induction heating. So in first one I am going to explain is pulse frequency control resonant inverter for different material vessel induction cooking or cooking loads. So this is the major feature of this configuration is actually we have to these resonant converters means automatically they will provide the soft switching, and this converter configuration is suitable for two different types of materials like steel and aluminum will took here. So for that one it is suitable, and the low component count components in this configuration is less only compared to the other, and here it provides the higher efficiency. So this is the proposed topology actually. So this is in this configuration. If we observe that actually we have two legs means four switches are there, and one switch is here. This is the in this one this is the buck boost type. Buck and boost both operations will be occurs here. This is buck boost configuration. So in this one, actually, when we see that boost operation will be operated because of the inductor and capacitors, and DC source will be the only one source we are using, and we are providing here double the voltage. Actually, this buck boost buck boost converter will change the polarity of the voltage. So that's why this VDC plus across this capacitor also will get the VDC. The total voltage across this leg is will get the 2 VDC. So 2 VDC voltage will be there. So in this configuration, voltage will be increased 2 VDC until it is provided to the two loads. Actually, two loads we are using. One is low frequency load and another is high frequency load. So this load is operated for, actually normally we have to choose induction cooking applications. We choose steel or iron loads have with operate with the lower frequencies only. Means why? Because they have resistance, internal resistance of that property of the metal is they will provide the higher resistance at lower frequency itself. But when we go for the aluminum vessel, if we choose check their properties with respect to frequency, their resistance is very low, very low. Actually means that is below 1. So that's why they'll draw the higher amount of current. That's why when we keep the aluminum vessels on the induction heater, means if in home we have that, that will not work because of that. That is reason. So in that one, their current limit they will provided. That's why that will show the error. So aluminum vessel loads up, draws the more amount of current. So when we operate for higher frequencies, their resistance will increase. So with respect to frequency, resistance of that vessel will be increased. So that is parallel, proportional to each other. So with the higher frequencies, aluminum vessel load will provide higher resistance. So that's why we are operating this leg at higher frequency to operate the aluminum vessel load. So this is the admittance curve of that, those two vessel, whatever we are to took that. So this is the low frequency, means this is steel vessel and this is the aluminum vessel. So this is the switching pulses. These are the high frequency switching pulses and low frequency switching pulses. When you observe that, means in this one also independent power control is possible because of that ADC control or frequency. Actually, mostly we use here frequency control technique. So frequency is changed. So from here the two frequencies we choose is 35 kHz and 150 kHz, and we operated here this FFTs I shown with the 40 kHz and 150 kHz, and this is 40 kHz and 160 kHz. Means different, means low frequency and medium frequency variations I shown here. So this is output control. If we observe with that, means these are the waveforms I shown, but here you can observe the curves. But with respect to frequency, current is varying, means with respect to whenever frequency is changes, then current this is with respect to lower frequency. When we observe here, frequencies are from 33 to 42 kilohertz. Here 148 to 157. So whenever we change the low frequency load frequency, when we change, then load current of that vessel only change. So independent power control also possible with respect to this converter. So that is the advantage of this configuration. So features of this configuration of switching we have achieved, and as well as suitable for two different types of materials and independent power control. This will show the independent power control, and this is low component count. Actually, when we go, actually how we can say the low component count here, because here we have only 4 switches are there to 5 switches are there to operate the two loads. So means normally when we operate for single load, we need 4 switches. So here we reduce the 3 switches. So that's why this cost effective configuration. So low component count, and this is cost effective also. So we achieve resonant frequency, resonant converter. So its inductive nature is there. So soft switching will get. So high efficiency will get in this configuration. So if we want to see the web, it will there in that. So 3 load cyclic control single stage AC resonant converter configuration. Next I am going to explain about this three load configuration. So in this one also we are using different loads, means 3 loads we use. Single stage means AC to AC converter configuration. So major operation is boost operation possible in this one, and soft switching for higher efficiency. And actually when we go for the single stage configuration, we use the series with the source. We connected series inductor and to get the boost operation, and the switches we are operating in the 50% duty cycle common leg. So we will get the double, means we can 0.5 duty cycle is there, so voltage will be doubled there, so output voltage will be higher in this case. The independent power control also possible in this configuration. This is the proposed configuration. So when we see this, this is the how many loads are there here? 3 loads are there with 6 switches. So leg 1, 2, 3. Leg 1 is one for load 1, leg 2 is for load 2, and leg 3 is for the load 3. And but these all loads are connected in same loads. We are not using different loads, not different frequencies. Multiple frequencies are not there. Same frequency we are using. And here whatever I spoke now, just inductor is connected in series with the source, so we can get here because of that inductor and this switch and diodes will get the boost operation, and we are operating this leg at 50% duty. So 50% duty means we get the double the voltage, whatever the two, if we apply the 200 means 100 volts, means we'll get the output voltage is 200, means that is depend upon the DC. Actually this will provide this, whatever this common leg and this diode will provide the rectification as well here. So rectification and inversion both will be possible in this configuration. So actually how you may get some doubt here, because of this diodes and this anti-parallel diodes with this rectification, and as well as with this switching, with the switching we'll get with that switching can get the what is the switching frequency is there. This load will be resonant with that frequency only. When inductors and capacitor will be there, for other frequencies it will provide the higher impedance, so that's why it will not allow the different other frequency component of current, but it will allow that whatever the frequency we are operating for that leg. These are the switching patterns for that to operate the independent power control. So here this is leg 1 switching pulses, and leg 2 and leg 3. So those are connected here, and we are phase shift 180 degree phase shift we are going, and in this configuration at a time only 2 loads will be operated. So at a time 2 loads, when we observe at that time T1 instant, load 1 load 2s are operated and load 3 will be off, means no power will be delivered to the load 3. And in this instant when we observe at T2 time, that only load 2 and load 3 will be operated, load 1 will be, and in that way we are providing the switching pulses here. So switching, that total operation of the converter is depend upon the switching patterns, how we are giving to that. So based on that only switching on and off will be there. So modes of operation. So here modes of operation is just like to explain the converter configuration. Just here this is switches. When this actually when these two switches are on, then this load will be powered. When those two switches are on, then this load will be powered. When this switch and this switch is on, then this load will be powered. So when we observe here in this configuration, this switch is off. This switch is off. So that's why this load will not be powered here, but remaining loads will be powered. And similarly in this case, these two switches means these two switches are on, so this is load is connected in between that, so powered here. And this here these two switches are shorted, so here this load will be short circuited here. And similarly in this case also, so based on that switching, means how switches are on, based on that only our power will be delivered to the load. So this is the waveforms I shown, whatever the simulation waveforms are. That means we'll getting in this configuration we are getting we'll getting unity power factor. Power factor is corrected, first point is, and then this is the load power current, load voltage and load current variations with respect to duty cycles. So whenever these duty cycles are equal, then load power will be same. For all the cases when we observe the pattern of that voltage, it will be same voltage and currents are same. So power is be delivered equal to the all. But that is average power amping. And load voltage means these are the expanded waveforms I shown here, how it will be there. Whatever the drawn means those are drawn in the drawn, but these are the simulation waveforms with respect to time. So at this instant, if we observe these two loads, this is the load 1, load 2 and load 3. So load 1 and load 3 are powered, and here load 2 and load 3 are powered, and in this case load 1 and load 2 will powered. 2 and 3 and load 1 and 2 are powered here. So this is the voltage and current waveforms. If we observe the current waveform also, here this sinusoidal waveform is there, but this is not sine, this is actually square waves, but because of the not proper choosing of that capacitor, it will be there, like that. So loud power control actually with respect to when duty cycle of that one, when we observe here this waveform, they here this average power will be high, means voltage waveforms are different. So most of the time switch on voltage and currents will be there, but in this case we check just 0.3 d1 is zero point 0.3 duty cycle. So because of that, so average voltage when we calculate, that is different here, so that is reduced. So power will be controlled based on that. Means when we change the duty cycle of the leg 1 d1, leg 1, their duty cycle change. In duty cycle we calculate for the leg only here, that is the symmetrical duty cycle wave only we can calculate here. So this is the load 2 voltage and current wave control with respect to duty cycle. And this is the load 3. So here we just to see observe that load 3 variation is there, voltage and current variation is there, then power is controlled. So in that way we can control the load powers. So load 1 power is controlled here using the duty cycle first, and that leg duty cycle, and this is load 2 power control and load 3 power control. So this configuration, if we observe this configuration, in this if you observe this configuration, just 6 switches are delivering to the 3 loads. So here again we have, if we individually if we operate the loads, then we need how many switches? For each load we need 4 switches. 3 loads means 12 switches, it means half of the switches we reduce, and as well as we are boosting here, boost operation is also there. That is the advantage of this configuration. Means in this way we have to analyze the converters, and we have to do the some innovation in that. So these are the features we achieved using this configuration. Boost operation suitable for two different types of materials, as we can it is suitable, but we have to choose the different frequency. Soft switching, independent power control, and component count will be less. So this is the paper you can see in IEEE. So motivation, actually these are the things we have discussed up to now for different, means these things we discussed about the multi loads as well as the multi loads as well as the multi material loads. So actually how to motivate to do the literature for the next how we have to do the for multiple vessels and different material vessel applications. So some converters here whatever we discussed, those have uh, means actually in literature so many converter configurations are there, but in that one most of the configurations are suitable for like ferromagnetic materials like steel and iron vessels. But aluminum in domestic uses we use mostly aluminum vessels, and in our home applications also we use aluminum vessel loads. So that's why we have to think about the non ferromagnetic materials like aluminum and aluminum and silicon, aluminum vessels, aluminum, and as well as uh, mostly in our applications aluminum vessels we use in domestic. So those have some high, they will not be operated with the lower frequencies, they should be operated for higher frequency, they have some limitations. So that's why we have to think about that. So from this literature I thought that some gap is there in that, so we have to do some research on that. So that research we have finded here, and that research objectives we took here. So and developed some multi-load outputs and suitable for different types of materials, independent control, and independent reduce the voltage stresses and soft switching as well as higher efficiency, and reduce the component count. So those things we have to, means those that gaps we found, and we did the research in that way. So here, and based on that, we propose the multi-frequency cascaded resonant converter for different material cell induction cooking applications. So major feature of this one is actually it is provided, it is in cascaded manner and reduces the voltage stress across the switches, and soft switching in high freak operation. These things will be, these are the common features for any converter. If we want to go for the higher efficiency for induction heating application and multiple loads, means we have to achieve these things. These things we have to consider. That is, independent control is must needed for that, and soft switching is must needed. Why? Because we are operating for higher efficiency and reduce the voltage stresses. Actually, whatever the converter configuration we discussed up to now, in that one voltage stresses will be somewhat higher. Because why? Because there only two switches are there. But when we go for the higher, means when we go for the more 4 number of switches, in that case voltage stress will be less. So that is the main thing. So voltage stress also we have to consider, otherwise switch may not will not be stand for that voltages. So we are choosing for, means when we go for the higher voltage switches, that cost is also increases. So based on that, we have developed one configuration here, that is cascaded manner. Two DC sources we took, and two inverters, and to power the three loads here. Three loads with different metals. So aluminum, steel, and iron we took. So iron, steel, and aluminum vessels we considered for this. This is the configuration proposed. This is the cascaded converter configuration. You may already study in that actually multi-level converters. So multi-level cascaded converters. But here that is not the same case. Here we are operating at different frequencies. Two cascaded bridges operating with different frequencies, low, medium, and high frequencies. So this high frequency is uh, is delivered power to the aluminum vessel, and low and medium frequencies deliver power to the iron and steel. So you may get doubt here why we are choosing low, medium, and high frequencies. So why? Because this iron load means I already spoke about this thing. So iron load is have higher resistance at the low frequency itself. We can operate this low iron vessel 20 kilohertz itself. We can get the higher whatever the magnitude of whatever the temperature we need across the load, that we can achieve using the lower frequencies. And using the medium frequencies you can achieve the steel vessel also, but aluminum vessel we can't achieve using the lower frequencies because it have lower resistance at the lower frequencies. Means below 1 it have. So below 1 means this 200 volts if we apply, then current if we observe that across that load current is very high in that case. 0.1 or 0.5 means double of that. So we'll get the higher current. It means that aluminum vessel load will draw the very high amount of current from the source, but we can't draw the more than actually in our home application sockets we can't achieve more than 20 amps. Means if we go for this one, 20 amps means 20 amp switches will be there, but the flux will be there, but that will it is draw the more amount of current. This more means for aluminum vessel if we check, that is more than 20-30 amps. When 1 kilowatt aluminum vessel also if we consider, their power is nothing but in aluminum in induction heat cooking applications, power is nothing but I square R loss only. Mostly that is depend upon the copper loss only, I square R loss of that vessel. So R is very low, but current R is 0.1 is there, means it have current should be higher. So then only maximum power will be get across that. So aluminum vessel loads will draw the more current per lower frequency. That's why we are operating this one is higher frequency. And load is here. These all are you may observe up to now whatever I discussed, those are the series resonant only, series resonant converter only. This is these are the gate switching pulses, means for that converter. This is VG1, VG2, VG3, VG4, means here total we have 8 switches. So 8 switching patterns I shown, and how voltage will be there and how current will be generated across that. So here resonant load, so current will be sinusoidal, but voltage will get voltage, output voltage depend upon the how we are switching that switching devices. So switching devices we are switching in that pattern, so then output voltage will be there. So like this is these are the voltage and currents will be get low, medium, and high frequency all are shown here. And resonant curves here there. So resonant curves, when we observe iron, steel, and aluminum, so these are the resonant things. Actually in this one we observe this resonant capacitor we have to connect externally to resonate at that frequency. Low frequency means we have to resonate at that frequency using the external capacitor. External resonant capacitor we have to connect in the circuit, but this L and C no need to connect the inductor. Vessel itself have inductive nature, means it is the secondary side we get the inductor, means because of that is in work as a coil, singlet and coil vessel. So inductor will be there, but capacitor only we have to choose and we have to connect externally. Okay, so these are the resonant curve for that different frequencies. So these are the load parameters we consider. And load parameters, I mean, this is the just 30 volts we did, but that with this with respect to different frequencies we choose, and here is 20 kilohertz, 100 kilohertz, and 400 kilohertz. So here why we are choosing in that way also, actually here frequencies are different. I'll explain here. So induction heating load characteristics, actually load we are choosing here, this is iron load. So iron load characteristics are drawn with respect to 0 to 200 kilohertz. 0 to 200 kilohertz. When we observe 20 kilohertz itself, iron load have minimum 2, near to the 3 ohm resistance is there. But here when we go for this steel vessel, it also have near to the 2 ohms. But if we observe the iron and steel, in between these two metals is some difference is there. So here this load have 3 ohms at the 20 kilohertz. This load have below near to 2 ohms, means 1 ohm resistance difference is there. Means metal property depend upon the frequency it is changing. So inductance and resistance both are changing with respect to that. So here if we check, that is with respect to frequency, what is the inductance at 20 kilohertz? At 20 kilohertz, what is the inductance? Inductance is almost, it is 80 to 9, nearly 90 microhenry is there. But here in this case, this 20 kilohertz, it is 67 like that. Means inductance and resistance both are changing with respect to frequency in induction cooking loads. So if we observe the aluminum load, so you get here clarity. Actually, this is I'll shown for 50 to 450 kilohertz. Below 50 kilohertz means it is less than 1 ohm. That's why I didn't shown here. We are operating this load at 400 kilohertz. So 400 kilohertz means it is at here 400 kilohertz. So at 400 kilohertz it is 3.5 ohms is there. For 20 kilohertz in iron load, 20 kilohertz itself we are getting the 3 ohms resistance. And inductance value also very less at 400 kilohertz. How much it is? Is nearly 50. In that case, it is 80 like that is there. So that is the difference. So inductor and capacitor values are different with respect to frequency, and we have to choose properly that values also. And if we will not choose the proper frequencies also, that harmonic component of current will induce. I'll show in that waveforms how it will be effects. So these are the actually cooking load behaviors I shown here. So here this is the 3 different frequency voltages are there. Across the load will get, this is across the load only. So from the source will get the DC, but across the load will get the different frequency voltages because of that switching pattern. So we are operating that let's say at different frequency. So different frequency component of voltage will be there. So low, medium and high frequency voltage will be there here. So low frequency voltage is applied to the leg 1, means load 1 only. That load will resonate with that frequency. Low frequency voltage only means that with respect to that low frequency voltage, whatever the current is induced, that will be allowed by this load. Why? Because this is resonant with respect to that frequency. Similarly, for medium and high frequency also, we have connected resonant capacitor in that way, and we have to choose the proper resonant capacitor. If we will not choose the proper resonant capacitor, then current will not be drawn by that load, and that current, those will not be operated. So that is the difference. Here this FFTs also means I'll draw, these are the visual drawn, but I'll show the waveforms also, whatever the simulation and how hardware results also how we took. So this is the low frequency, medium and high frequencies. So similarly here, just I shown here with respect to low frequency voltage how those load behavior, with respect to medium frequency how their behavior, and with respect to high frequency how their behavior. Like, so modes of operation, in this one different modes of operation we consider based on the uh, switching pattern, means how we are switching the switches, means we have to analyze these things. This one it is take a lot of time to explain this thing, but here I just simply I will show that only few modes I shown. So the S1 and S4s are on, means these switches are on. So actually current will flow in this way, and these switches are on means like this. Means these two voltages are connected in parallel, and these switches are operating at different frequencies. So that frequency component of voltage will be generated here, and output voltage will be sum of these two voltages, that is 2 VDC. Like that different voltage magnitude will be there 2 VDC. That's why in that waveforms also whatever I shown here. So here also you check with this 2 VDC, VDC and minus 2 VDC voltage patterns will be get, magnitudes will be get different voltage, and voltage 0 will be also get. So that is the different voltage magnitudes will get across the load. So that is also depend upon the what is the switching pattern, how we are connecting the switches and how we are switching the switches in the converter. So I'll show that is those are in simulation and experimental results. So here in this configuration we can use the asymmetric duty cycle. So duty cycle we have to change, we will not operating with the frequency, we are not changing the frequency. Why? Because we do not have that, here 3 frequencies are there and we do not have that much difference. Actually multiple frequency, third and fifth harmonic currents may induce and that may affect. So that's why I chosen here asymmetric duty cycle to control the power. So these are the simulation and hardware results shown that. So this is with respect to fully duty cycle. Fully all legs are operating at the full duty cycle. So DL, DH, DM and DKH both all are operating at 0.95 duty cycle. You may get doubt here 0.95 why, because actually we have other things that rise time, fall times are there, dead time will be provided. So when we do the hardware, then we have to choose all those things in proper way. Then only will get the soft switching and as well as converter will operate. Otherwise, will not get the waveforms. So this is the total current. I shown here this is load voltage, whatever the across the load when how much what is the voltage we are get, that is the voltage, and this is the total load current, and this is the low frequency, and this is the medium frequency, and this is the high frequency currents. So when we observe the waveform shell, we can see that this is the low frequency. Frequencies are less. So here a number of times it is on and positive negatives are there. Means this switching means higher frequency it is there. This is low frequency. This is very high frequency. This is 400 kilohertz. So here this is their FFTs. Whatever I shown, that is the same simulation and hardware is hardware waveforms here. So whatever I captured using the MDO, that is here if we observe that this low, medium and high frequencies are only there here. So remaining component of currents are zero only. When we change the frequency, those frequency component of current will increase. That's why we are not choosing the different frequency control technique here. That's why we went for the ADC control. So in ADC control, frequency will be fixed. So that's why that will not affect on the that different frequency component of currents. The next one is this is I control whatever the duty cycle I changed here. Medium and high frequency I kept as constant, and but low frequency duty cycle I changed to 0.2. So then this, if we observe the waveform here, this is the current is reduced. These are the current waveforms only, low frequency current and medium and high frequencies. So I didn't show this output voltage will be same only, but that pattern will be same, but magnitude will be changed, but pattern will be same. But here voltage current magnitude will be reduced here. Magnitude of current is reduced. So low frequency remaining two components are constant only. When we observe the FFT, it will be clear. So here it is low frequency is reduced, medium and high frequency are constant only. Similarly for the medium frequency, so their FFT also here, this FFT, this component of current is reduced, and here this is reduced, and these two currents are constant only. So like that for medium frequency and for higher frequencies also, so these two currents are fixed, but this current will be reduced here. So in that way we can control the output power using the asymmetric duty cycle. So this is the independent power controls. So with respect to duty cycle, those will be changed. So for different frequencies and different duty cycles shown here, and these are the efficiency curves. This efficiency also, you may get doubt here why we are operating at higher frequency, why it is not affecting on the efficiency. Efficiency is also affected because of the higher frequency load only. Because of high frequency load, so high frequency load have higher means will not get pure exact soft switching here, because of the multiple frequencies. Some at some instance will not get the switching, will not get the ZVS. So that's why switching loss will be high, minimum little high in the high frequency case. So that's why the high frequency load efficiency if we check, that is nearly 90 only, but in this case it is more than 90 will get. This is the how we did the experimental waveforms. So the experimentation. So experimentation. This is two DC sources we take, and this is the control driver circuit, and this is the converter here, and these are the three different loads: iron, steel, and aluminum load. And this, here the capacitors also connected. CR1. This is the resonant capacitor 1, 2, and 3. These are externally connected, and this is our converter here. This is our converter. So this PCB also we designed ourselves, and we did like this. So here actually we have 8 switches, so 2 gate drivers are we use. So gate driver designing also very crucial, and we have to choose in proper way how we have to isolate, and means isolated gate drivers only these are. So isolation we have done using the optocouplers. So optocoupler based gate drivers we use here, and the transformer based means optocoupler driver circuit also there, but that is somewhat inductive nature, so in that complex, and that is costlier. So but here we are using optocoupler based, so optocoupler based gate drivers, and here we are using different optocouplers and different drivers ICs, and power control we generated, gate pulses we generated using the microcontroller. Here we use DSP board. DSP, in that DSP means in that one microcontroller only there, DSP control board we use. So TMS 320, in using this one we provided the gate pulses. So whatever I shown the gate pulses we generated using that. And in that one also just we used Simulink blocks to generate those. Features of the proposed configuration. It is already I shown that it is working for multiple vessels, means ferro and non-ferromagnetic materials also, independent power control and efficiency also we get from. So limitations of the, these are the, no, here whatever we shown, that is the DC supply we given, and there DC is converted into AC. But in our home application, when we go for the domestic use, our supply is AC only, but we have to use one more rectifier before that. Actually, when we see this configuration, so when we see this in this one, actually we are taking DC source. We are not plugging from the source, whatever the supply we are getting in the room. But these are the different DC sources. These sources itself very costly, and we have to use those sources. But rectifier stage is not there in this configuration. So rectifier stage is externally we have to add, and we have to give the DC supply. To avoid that limitation, we proposed here single stage converter configuration. I already spoke when I was different schemes. In that case only I told multi-stage and single stage converter configuration will be there. So single stage converter configuration will not need any rectifier stage. So in built of that converter itself have inverter and rectifier both. So that is the limitation we achieved from that configuration. So we proposed a configuration, that is single stage AC resonant converter for different metal vessels. So this is the major features of this single stage configuration is it is boost operated, single stage AC to AC, and soft switching for higher frequency also will get soft switching. Soft switching anyhow in resonant converters will get soft switching because of the load nature itself. It is load resonant, but in AV applications, when we go for the electric vehicle application, their load is not a inductive, but inductive nature we have to create, means we have to connect externally that L and C elements. But in series resonant converters, no need to connect, means actually series resonant means we have, if it is inductive nature load is there, means just we have to connect the resonant capacitor only. But in EV applications we have to connect both L and C values, we have to choose in proper way, and we have to design in that way. Otherwise it will effects on the all the leakage inductance, magnetizing inductance, and as well as that frequency dependent. So in our circuit different frequencies are there, because of the EMI issues some parasitic will be added, so parasitic inductances will be occur, and that will affect on the that affects on the inductance value whatever we are connecting. So that their choosing of the inductor and capacitor is very difficult. But in series resonant converter, that just we have to choose the resonant capacitor only. So resonant capacitor we have to choose in proper way to get the resonant frequency. So in single stage here we'll get a soft switching, boost operation, and suitable for different metals. Same those features will be occur here. So in this proposed is actually using only single converter to to deliver the power to the two different loads, aluminum and steel. So load equivalent circuit is shown here. What is the normally our induction heating load will be like this only. So this equivalent inductance will depend upon the omega mutual inductance R2 and whatever the inductor resistance is there, means across the secondary winding whatever will get. Secondary winding means it's just single turn only here. So this is the structure of multiple load. This is multiple load, but actually multiple load means we have this all stages. But here just one converter stage to supply the provide the supply delivered power to the two loads. So this is the proposed configuration. So I already shown there a single stage 3 legs, but that is not suitable for multiple vessels, and that configuration we development there, that configuration also suits for the multiple vessels, but we have to choose the proper way of independent power control and control technique we have to choose in proper way, otherwise that will not work. But here in this configuration, if we check this is same, that configuration, this one is same, but here we are operating two legs at different frequency, and control also we use here two different frequencies we are using at multiples of 8, means first frequency we chosen at some 20 kilohertz, means higher frequency we chosen 160 kilohertz. So it will not be induce the other frequency component of currents. Because of this frequency, it will not affect on this. This frequency will not affect on that. So to avoid that, we choosing the band, different band, means large band in between these two. So these are the two loads we choose in. And actually this is here also we'll get this diodes, and this anti-parallel diode provide the rectification, and this common leg will involved in both rectification and inversion. This inductor is boost inductor, and boost capacitor will be connected here. This is the inverter switching pattern. So here connected this VG1 VG2 are low frequency, and VG3 VG4 are higher frequency. Output voltage will be like this. So we are operating multiples of 4. Actually 20 kilohertz means 4 into 2, that's why your 4 pulses we are getting. So this is the 20 kilohertz pattern, but this square waves are for 160 kilohertz. So here which is in 20 and 160 kilohertz. So this is 60 and 1 steel and aluminum. Steel vessel is operated at the 20 kilohertz, and this aluminum vessel is operated at 160 kilohertz. So these are the load equivalent already whatever I shown. 20 kilohertz, how inductance and resistance will be there for the vessels. So steel vessel we took, and for the using the LCR meters we measured this value for that vessel with respect to different frequencies. And we characteristic drawn here. So this is the load behavior with respect to load frequencies, and how converter will be operating different modes of operations I shown here. Actually in this configuration, if you observe that how when switch is on, diode is on, how it will be there, and here whenever both switches are on, how it will get short circuited, like that. Means in this pattern how we are getting this voltage. So in this case we'll get that both switches are on. Actually S1, actually when this S1 and S3 are on, S1 and S3 are on, at that time how it is there, voltage will be 0. And like that, means based on the switching pattern only that voltage will be induced. So we have to choose a switching pattern in proper way, how we are connecting, how we are switching that switching devices, how we are providing the delay, and how we are providing that rise time, fall time for that one. Means everything we have to consider while designing that. But in simulation we'll get a anyway, but in hardware when we do that, means a prototype of that any converter, then we have to choose everything in proper way, and we have to choose our gate driver also proper way, and PCB also we have to design in compact way, and as well as how to consider the EMC EMI issues also in that case. And filters also we have to connect a series. Here we connected the filter, but I didn't shown here, but filters also we have to connect to filter out those harmonics. So here I shown this is the converter. These are the different modes of operation. So here different modes are there to how it will work, and these are the simulation experimental results. So in this configuration we will got the power factor correction. Actually this configuration now, that is the main advantage, power factor correction. The load is have inductive in all these configurations. When we do here, we observe the external experimental waveforms also will got the exact unity power factor. And boost operation also, actually we operated to 40 volts, but here 80 volts we got. So boost operation is also there, means 0.5 duty cycles we are operating, so boost is there here. So boost operation, so simulation experimental both you can get here same. And here this is the output voltage waveform. So with respect to output voltage, low frequency and medium frequencies. So these are the expanded waveforms also shown here. Whatever the in Visio how it run, those things will get here. The simulation and experimental also. And this is the low frequency current, and this is the high frequency current. So actually this is the output, the total load current. Total load current have both component of currents, both are equally operated. But this you may get doubt here also. Actually here FFT for 20 kilohertz it is showing the some 10 amps, and here also how it is done, means that we have to choose using the resonant capacitor. Resonant capacitor we have to choose in proper way, then only we'll get the exact values. Otherwise we will not get. Means resonant capacitor we have to connect in different series and parallel combination. I'll show how we connected the resonant capacitor. So here we use the MKP, and for lower frequencies we'll use the MKV capacitors. Actually capacitors have different. MKV capacitor means they have some higher voltage ratings, higher voltage and high current rating. But MKV normally in market will get here. Those are have lower voltage and lower current, voltage and lower current applications only. So we have to choose in proper way, then only we can get here this. So here load power control also, So power control is using the frequency. Here we use the frequency control. Why? Because here we band we choose n means 20 and 160. So multiple of 3 or multiple of 5 also it is not there. Multiple of 3 is 60 kilohertz. Multiple of 5 means it is 5 means 100 kilohertz. Multiple of multiples of 8 we consider. So that odd harmonics and not occurred in this one. That's why you can get here only that component of current only. Actually we just use, if we see this here simulation and hardware, only that component of currents only there here, low and medium frequency component of currents only there, but no other frequency component of currents. So that will not means other component of currents induced means that is the harmonic only, that will affect on other components whatever we are connecting in the circuit. Those are frequency sensitive components will be there in the circuit, those will be changed. Parasitic will be changed, any parasitics will be changed. So output current with respect to 160 kilohertz is shown here, and this is with respect to frequency control. How we are controlling frequency change 25 kilohertz. So here 25 kilohertz we did. So at 25 kilohertz, how it is changing? Only that frequency is common. Means leg one frequency FL we are showing low frequency we changed to 25, but high frequency kept constant only. So that's why that frequency component of current is constant only. So that power is constant, but this current is changed here. So in this waveforms also you can observe that how we are changing, how it is reduced. So this is a reduction in that magnitude also. So here the experimental also will get like, so at 20 and 165 kilohertz, just 20 kilohertz means this 20 kilohertz, this frequency component of current is constant only, but this is changed. And you can observe here also, that is when we changing the frequency to 65, 165 kilohertz, this frequency, other frequency component of current is not there here. So that is not inducing. But a little in the, actually when we see the experimental waveform, that is in that one also not much variation is there, just little bit. This is fifth harmonic component will be there, but that is even though we are choosing 8 multiples of 8, then also we are getting some minimum. Means when we will not choose the proper frequency, then how it will affect on the resonant frequencies, how it is affect on the converter can observe. These are the independent power control curves I shown here with respect to frequency 20 to 160 kilohertz, how it is varying like. So this is the efficiency variation. Efficiency means just only because of the higher frequency that variation will be high, but a lower frequency variations the efficiency will be very low variation, 93 to 92.5 to 93 degrees. But here you can, if you observe that 92 to 93 means that variation will be different. But higher frequency variations will affect on the switching losses. So switching losses will be high somewhat compared to that. So this is the experimental setup for this. So we Arduino we used here. So Arduino, to generate the pulses, and delay circuits are there. This is supply for these drivers. We need actually for these microcontroller, and as well as for this one we need some supply. So again delay circuit. So for that one this small DC source we use. But as normally in our industries when we are doing there, we auxiliary power supplies will be there. Means auxiliary power supply also we have to generate from the same source only. For that one different circuits will connect, like voltage regulators we use, and to provide that one, those things. Then this is the different two vessels we connected, and here only this is the gate driver and this is the circuit. Actually we, this is the gate power circuit. So power circuit with on PCB we learn, and these are the resonant capacitors for different loads. So these are the features of this proposed configuration. This is a very good configuration, boost operation as well as different metal. Actually, one major advantage is we have only 4 switches, and PFC is also there, and no rectification is needed. Directly we can use this converter for domestic application, and suitable for multiple vessels. That feature also there. Independent power control we are achieving, that is not affecting much on that frequency, even though we are using the frequency control, that is not not affecting. You may get doubt here why you are not using the other frequency controls. Actually that is the main disadvantage of this configuration. That is actually when we use the other frequency, this is not the full bridge, so phase shift we can't use. Asymmetric duty cycle if we use, then one load frequency control we can't do. Means power control is effects on the other one. Means one leg is common for both loads as well as rectification and inversion both. So that is the main These are the conclusion. Discussed the multi-stage and single-stage converter configuration. So here in this one, actually, I just mostly concentrate on the whatever the resonant converter application are there for induction heating application. But these resonant converters are not only related to induction heating; those are mostly using in the electric vehicle applications. Actually, whatever I'm doing in the here value, we are working for different converter configuration for onboard chargers. Actually, onboard chargers we are designing. So in that one, we are using mostly LLC circuits, CLLC circuits, LLC circuits only we are using to transfer the energy from this converter to rectifier stage. So in that case, we use some LLC, CLLC circuits in the inductor and capacitor we choose and properly, and we designed in that way. And we are operating for those are for the not for the 1 kilowatt or 2 kilowatt. We are operating for actually 4 project is there. One of them means different electric vehicles in industry. So many are there, but in we are doing for different different electric vehicles means different vendors actually like Ford as well as BMW. For that one, we are designing a 20 kilowatt 100. Now we are going for 100 kilowatt onboard chargers also. So I'll tell about those things. And whatever the features we have discussed up to now, whatever the configuration we discussed, configuration 1, 2, 3, those are actually DC, two DC sources. So is there in that one DC source we are using, and one is in one of the configuration only AC source. These are the main features of that configuration. So that these features we achieved using this, and these different loads we are used, so different metals and different frequencies, and number of switching devices in some configuration are less, some are high, like that. In configuration, in all this configuration, this is single stage configuration have more advantages compared to all. Why? Because it is power factor correction is there, as well as multiple load capability is there, and different material vessel capability is there. Number of loads also we are using two, and if we want to increase more than two, also we can use using that configuration. If we add one more leg, then we can add one more load also. So like that means multiple loads you can conduct. Independent power control we achieved. Number of legs only two in this one, so switches are less, cost of this converter is less, as well as losses also less, and everything is there in that. And switching devices are low, and here only drawback is PFM means frequency control we use. And what is the drawback? What is the main drawback of frequency control is that is frequency. When we change the frequency control, when we go for the and means if any frequency sensitive component is there in that circuit, means that will affect because of the frequency control. So that's why we can't go for the higher variation in the frequency. So that is a disadvantage in that. And efficiency also we achieved 94. Actually, if we design, then we'll get the 96, 97 efficiency also in that one. So these are things in that. These are the references. Thank you. And one more thing I want to say is actually here I discuss only the induction heating. So actually in domestic uses, no trend is for electrical engineering. Lot of openings are there in industry also, but in industry, those who want to work in industry, you have to think about the resonant converter. Resonant converters applications are more in the industry for electric EV applications. So in EV applications, they're using the three means actually three element, two element I discussed, no? Two, three element converters they are using. For LLC inverters are more advantageous compared to that. So they are providing higher efficiency as well as a higher efficiency, high frequency. Means when we operate for the higher frequency, what is main advantage is we are reducing the size of the passive elements. So size of the passive element is reducing means cost of the element is reduced, and the size of the converter also means whenever we are operating at a higher frequency, main transformer size is reduced there. So transformer size is reduced means that is the major achievement of that converter. So in transformer is the bulky in our any converter configuration. So transformer we have to size reduce means we have to increase the frequency. So that's why in EV applications, when in our applications mostly we are using 200 kilohertz also resonant converter, three element resonant converter we are using for more than 200 kilohertz also to reduce the size of the transformer. But not that is not the easy to achieve everything there. But when we are operating at higher frequency means we have to control proper also. So that is there. So we are here, we are mostly we are doing on the different vendors, like a different power values also, means 22 kilohertz, 11 kilohertz, 20 kilowatt, 11 kilowatt, and 100 kilowatt also. Inverters we are designing for more than 800 kilowatt also for the uh, whatever for that drive systems. So inverter designing also we are doing, but that is very different. But in that one, mostly resonant things also we are considering, but we are not much in that one. But in onboard chargers we are doing 100 kilowatts also with respect to with using the CLLCs. Okay, thank you. You have any doubt?
Thank you, sir.
Okay, thank you.
Thank you, sir, for sharing your thoughts on resonant power converter configurations for high frequency applications. And also, you have given the scope of resonant converters, various combination of converters like two, three more, introduction of induction heating, and various control techniques for the induction heating. And also, you have given the great idea for those who are want to work in the industries to work on the size of the elements. Thank you, sir. Participants, if you are having any queries, you can unmute yourself and you are free to ask.
Good morning, sir.
Good morning.
Sir, actually, you told that load affects the resident converter performance. No?
Yes.
So in case
Actually,
of
actually in induction heating only load
induction
means.
heating, yeah, induction heating only I'm talking about.
Okay.
So what about actually when you are using in normal utensils in domestic cooking? How about the efficiency, sir?
Actually, material means different metal vessels when we use, if we want to use, means actually steel and iron, aluminum. Mostly in our domestic use, we use those. But when we
Okay.
want to use that one, so actually, for if we have, our converter is like that, so it is provide both, deliver power to the both steel and aluminum thing. So in that case, we have to means when converter itself they design the, we have to design the converter itself with resonant capacitors in proper way. For aluminum, we have to choose in proper way. It should work for that one only, in that band only. Otherwise, if we will not choose in proper way that resonant capacitor, that will affect on the means other load also will operates, means that will also operates because of that frequencies. So that resonant capacitor is plays a major role in that case. So resonant capacitor we have to choose in proper way. So that is the only case when we use for the different metals with a single converter. But mostly when we want to design for only aluminum vessel means that will not affect that much. But we have to choose the whatever the vessel properties means bottom of that means actually whatever the we designing the coil, that coil size depends on, and that size is most effect on the bottom of the vessel. So bottom vessel whatever it is conducting means what is the same phase with that, that will be heated, because of that in that portion will be eddy current losses will be there more.
Now, in case actually, is it economical to use induction type cooking compared to the gas?
It is more economical, but actually major problem is in that cases in our in domestic uses whatever we are using, those are no technologies not much improved and no new converters are came. Actually whatever they previously whatever are there, those are multi stages. So multi stages are there, that's why their cost is itself somewhat higher. And we buy those things, those cost is self higher, and they are actually induction heating loads are higher power loads. Actually 1 kilowatt is minimum needed for
Okay.
1 kilowatt, but actually whatever we are using those efficiency also 60 to 70% only. 60 to 70%. When we go for the 90 above efficiency, then those are economical. Whatever in the market those are available, those are their frequencies are not more than 80%. They're less than 80% only because of these stages. And there they use only single switches, but remaining things are high in that. So that is the major drawback of that. So that's why the people are not going for that. But in industry, I mean, like higher power ratings are there. In that cases, they are using in the different countries. They are using induction heating also. That is economical compared to these all.
Does they impose any harmonics into the system, sir?
That is there. That's why we have to provide the power factor correction also. Means input side filters we should connect. Otherwise, it will load is inductive nature. It will affect on the
Yeah.
harmonics.
Yeah. Thank you, sir.
Thank you.
Still, anyone is having any doubts from the participants? Any queries from the participants? Thank you, sir. I think everything is clear for them. Thank
Yes.
you, participants. The feedback link has been shared in the chat box. I request everyone to fill this feedback form. And with this, we are going to end the sessions of this FDP. After, we will be having the validatory function. After that, we will be having the assessment test on this FDP. So I request all the participants to join for the validatory function at 2 p.m.
Okay, ma'am. Can I leave, ma'am?
Yes, sir, you can use.
Thank you.
Madam, at what time we'll have exam, madam?
After the validatory function, ma'am, like it may be taking 20 minutes, 15 to 20 minutes. After that, we'll be having the exam at 2:20 to 25.
Okay, okay.
I'll be sharing the Google form in the chat box itself for the assessment test.
Madam, actually, I have invigilation in the afternoon. So I'll be in invigilation from 12:30 to 3:30. That is why I wanted to know when the exam will be.
Okay, ma'am, like you can message me in the WhatsApp number. To my
Okay.
WhatsApp number, I will be sharing you the link of the exam. You can
Okay.
write after the invigilation, ma'am.
Okay. Okay, madam. Thank you so much.
Okay, ma'am. Now all the participants can leave after filling the feedback form that is available in the chat box. And I request all the participants to join for the validity function by sharp 2 p.m. Thank you all.